In this video, I'm going to demonstrate how to perform an independent sample t-test on ranked data. As mentioned in a textbook, there is evidence to suggest that the t-test actually works fine on ranked data and that the p-value you get is actually fairly accurate. And so you don't have to do a Mann-Whitney U, which gives you a chi-square value and that you have to then transform into an eta squared. Now, in a program like SPSS, you still have to do that. But in order to conduct an independent sample t-test on ranks, you just need to convert the dependent variable data into rank data, which is very easy. Just go into Transform, click on Rank Cases, and then insert the variable of interest that you want to rank. So desire for physical exercise, put that into the variables box. And now you can see assign rank 1 to the smallest value, or you have the option to do it for the largest value. Now it's up to you to decide how you want to interpret your data, whether you want a rank of 1, 2, 3 to indicate great performance or indicate a high level of desire for something. So in this case, assign rank to 1 is going to the smallest value, which will actually suggest that the person is very interested in engaging in physical exercise, because the scale of 1 to 4 for this variable is such that the person wouldn't be very interested if they scored 4, but they'd be completely up for it if they scored 1. So I click on OK, and SPSS creates a new variable automatically, which has a lot of decimal places, which I'll get rid of. SPSS called it rank of V16, which is this variable here. So everyone who scored a 1 actually has a rank of 145. And that's true because there were ties, and so SPSS had to calculate the ranks such that there was an average taken from those ranks, and that average rank was given to everyone with a 1. Now 2s got a rank of 690. So all the 2s for MEQ16, every person that scored 2 got a rank of 690 in this data. So if you keep scrolling, 3 got a rank of 1,478. And then 4 got a rank of 2001. So not many males responded 4 as a response, but they got a rank of 2001. Now, females get the same sort of ranks. It's all 145 for someone who scored 1, whether you're male or female. Females also who scored 1 got a rank of 145 because it's a ranking on the entire sample. So 1 to 2,135. But again, there are so many people that score exactly the same score that the rank has to be averaged across those, and everyone gets the average rank. And then you can just conduct an independent sample t-test on the ranked data, and you'll get a mean rank from that. So go into Analyze, Compare Means, Independent Sample t-test, and I've already got the gender variable and the grouping variable, and I've defined that 1 and 2, males and females, and I put the rank variable in there. Click on OK. It's actually going to do the bootstrapping because I actually did that in a previous analysis, but we can look at the data if we want to. The simulation research suggests that even if you don't use bootstrapping, with an independent sample t-test on ranks, the p-value will still be accurate. So the mean ranking associated with this analysis: males 954.46, females 1,174.04, and the t-test is associated with a t-value of negative 8.936, and the p-value is much less than 0.001. And the bootstrapping version of the same analysis came up with a p-value of 0.001 exactly, whereas in asymptotic normal distribution theory it was p less than 0.001. So that's how you can do an independent sample t-test on ranks, and there's research suggesting it's totally fine to do so. With the asymptotic normal distribution theory approach, the p-value is essentially accurate. If you feel uncomfortable with that, well then you can do it with bootstrapping, and bootstrapping on ranks would work fine no matter what, because bootstrapping doesn't assume any level of measurement, so you have the option of doing either.